Hello guys, today I want to talk about IR compilation and explain what it generates. A Solidity compiler has a concept called intermediate representation, or IR for short. It's a pretty common compiler process, where instead of directly converting source code into machine-like code, you instead compile it into intermediate semi-low level language first, and then compile it into assembly. This happens for languages like C# and Java, for example. In the case of Solidity, code compiles into UL. This allows for more efficient optimization of the overall code, because of additional UL optimizations that can be performed before compiling into assembly and optimizing one more time. So let's take a simple contract. If we compile it like this, we would see a UL file was created in the output folder, and oh boy, for 10 lines of code it generated almost 300 lines of UL code. I guess we can call it an optimization. Now I want to explain everything that's happened in this scary UL code, so please keep children and pregnant women away from the screen. We can divide the resulting codes into two parts: deployment code and runtime code. Deployment codes will be triggered once during deployment, yeah, no way, and runtime code will be triggered during any interaction with a smart contract. Let's investigate the deployment code first. I will try to explain it. Let's start with the first lines. An object in UL is just a top-level container that specifies where we'll write the code. We can specify a name for it, and it's not just useless metadata. I will explain why later. Here we store the free memory pointer. First we use the memory guard function. It's a pretty simple function, and what it does is give us a pointer to a place where the specified size is available for us to use. Then we take this pointer and store it at the x40 memory address. Next we see a string check for call value, and then a revert. This is the code that basically ensures that the deployer won't try to send message value during deployments, and will revert if it sees that it's not 0, because our constructor is not payable. The strange hash after revert error is a catch 256 of the error message either sent to non-payable function. You can check it yourself. You can see this logic inside IR generator CPP in the Solidity compiler. After that the constructor is called, but because it's empty nothing will happen here. Now to the harder code. Allocate unbounded just gives us the free memory pointer that we stored before, and we assign the _1 variable to it. Then we call the code copy, and that's the logic where we basically load our runtime code. The functions datasets, dataOffset, and code copy are used to access other parts of UL objects. Datasize and dataOffset can only take string literals, the names of other objects, as arguments, and return the size and offset in the data area. With dataOffset and data size, we basically define where our runtime code is stored, and how big it is, so we can store the runtime code as a free memory pointer. Example 14 deployed is the object name of the runtime code. I promise it's not just a metadata and will be used in code. Now to the runtime code. First we do the same thing that we did before, store the free memory pointer, and then we check if call data size is less than 4. Why do we do that? To check if the user calls function or not. Because in order to call a function, the user has to provide at least 4 bytes of data that will correlate to a function selector. If it's less than 4 bytes, we revert with this error. The hash is the catch 256 value of the error contract doesn't have a fallback nor receive functions. If the call data is less than 4 bytes, or the provided selector doesn't exist on the smart contract, execution will be reverted with this error. Then we extract the selector by shifting right for 224 bits, which equals to 28 bytes. What it does is leaves the first 4 bytes of call data, which allows us to see what function selector was used. If no function is matched, the execution will be reverted with the same contract does not have a fallback function error. Now let's get to the function implementation and start with value. First we have the same call value checked to ensure that message value is 0 for this view function call. Then we attempt to decode an input parameter, but because value doesn't have any input params, this function is useless. I will talk about it more when we check the setValue function. After that, getFunValue3 is called. Here we take offset and slot as 0, because value is the first and only storage variable available, and because it's not a dynamic type and occupies a full slot, offset will be 0 for it, since we don't need to shift any bytes before accessing the full value. So during the extract function call, shift right is useless, but if we had two uint 1 to 8 variables together, instead of one uint 256, we would have these values instead. Also you can see a cleanup function being called. It's also useless in our current scenario, because no cleanup has to be done. But it would be useful if we were to convert different integer types, for example uint 1 to 8 into uint 256. In that case, cleanup would look like this. Transform if it's not really obvious why this is happening. because these useless functions are made to make all the paths follow the same flow of function calls, even if it will be useless in the end. When we've got our storage value, we have to store it in the memory before returning it. That's why we take free memory pointer and then check how much space we occupied using the IB_encode tuple function. So we just store the value we got from storage at the free memory pointer, and in the end we return the data from memory and end execution. Now to the set function. Like we already did, we check that message value is 0, and now we can talk about what happens during the IB_decode function, since we accept the parameter this time. First of all, we ensure that provided parameter is a size of 32, because VUN256 has a size of 32 bytes, and if you try to pass the value with a smaller size, it means that you are attempting to provide an incorrect type, and transaction should be reverted. The revert error is catching 256 of the message ABI decoding tuple data too short, because the param occupies a fully memory slot of set is set as 0. The last interesting thing here is the validator revert check. Here we check that the provided value is cleans up, because otherwise the provided param is wrong. The cleans up value ensures that the value is in bounds and correct. If it's not equal to it, then something is wrong. Now let's check the logic that actually updates the storage value. What it does in general is just try to clean up and convert types to each other, to ensure that the value we want to set into storage would fit into the slot and would be clean. All of these conversions are useful mostly for cases where types are different, like I've mentioned before, in the case of cleaning up values. Here it's pretty straightforward. We just do store into the first slot with the parameter that was provided by the caller. In the end, we just return empty data, because our function doesn't have a return value. The last thing that we see in the code is metadata. It simply contains all the info about how the code was compiled, so it can verify it later on scan, for example. That's about it. If you have any questions left, please leave a comment down below. I know that some things I could have explained unclearly, so having a question is absolutely normal for this type of content. Thanks for watching, and have a nice assembly reading day.